Challenges in the future of machine learning. We have a diverse West Coast panel from Seattle to San Diego. The way we thought we'd structure this is each panelist has been charged to, and here we have one more to join us, to tell us what they think are one or two important computational challenges with machine learning in mind, and what the future might bring. And they've been given a cap of 5 minutes. So the plan is to let them go through those. If you have a pressing question that must be asked immediately, please do, but otherwise we'll open it up for questions after they're finished. And in completely random order, I will ask Yoav to kick off.
Okay.
Yoav Freund from UC San Diego, who's been a pioneer for machine learning theory and a hero for me.
So, so I think that you can think about various things that are important for machine learning, but I think that what emerges for me in my work in the last few years is that communication is at least as important as computation. So when we basically think about distributed algorithm, which we are now all the time thinking about because that's the only way to work with these very large data sets, the question is how much can we, what is the least amount that we can communicate and still achieve our task? So in general, we think about communication as something that happens in the background, doesn't really matter. But if you think about the barrier model, that is the current most used model, in which the workers work in parallel and then report back to the master, there the communication scales with the number of workers. And so if you start to have too many workers, the time to communicate dominates the time to compute. And I know it from experience because I've been running various tests on my Spark cluster, and it seems like no matter what I do, the average load on the CPUs is around 5%. So something else is blocking it, and it seems like it's the communication.
Great. Moving right, we have Maryam Fazel from the University of Washington, optimization expert among other things.
Hi. So my background is actually in optimization. Before that was also more electrical engineering, so signal processing and control. So I'm newer to machine learning. I've learned a lot of machine learning by participating in this sequence of workshops and the program here at Simons. So one thing I wanted to mention that I have seen in talks that came up is, from the point of view of optimization, is that we understand convex optimization problems fairly well, but a lot of problems that arise in machine learning are not convex. So people nowadays are talking a lot about non-convex optimization. But the problem is saying something is non-convex is not saying anything about it. So we need to start to actually formalize a set of assumptions of how we are going to go away from convexity. There's a lot of recent work in this area, but there's still a lot that is open. Some of the recent work have been on very specific problem structures and cases where then you can say a lot under strict assumptions. For example, you can even say that the global optimum of an optimization problem can be reached by a simple algorithm, you can reach the global, and so there's no question from a certain type of starting point, for example, that you can generate for that type of problem. But the setting in which this works is very restricted. For example, like dictionary learning models or things like that. What about more general problems that don't have all those assumptions? There you might have problems in which you have many local minima, but you want to have a way of saying what is a good solution for my problem. Is a local minimum good? Is a particular type of local minimum good? So these are questions that are still open. So for example, from machine learning perspective, you may not want the global minimum if the global minimum is a very deep and narrow type of minimum. maybe you are more interested in flatter, broader types of local minima. So characterizing what is it that we want from the solution, which also relates to what you do with your model afterwards, like generalization, for example. That's another issue. And from a computational point of view, two big issues in non-convex optimization are the fact that setting the step size in an iterative algorithm is not obvious anymore as opposed to convex optimization. And secondly, that stopping criteria is not obvious. You don't know exactly when to stop. So the question then boils down to what kind of subclasses of non-convex optimization problems can we study for which we can say something systematic about these questions. So, and I can discuss it more if there's interest in specific questions.
Wrapping around, we have the Karp from Berkeley. This must be a high point of his career as director of the Simons Institute.
Absolutely, high point. Since I don't work in machine learning, I won't say anything very deep, but I would like to share a few impressions, if you will, of an outsider to the area. So the usual model of supervised learning is very, very general and simple. It's the problem of inferring a function from values at a set of sample points. To give the setup in complete form, you have to specify the training data, the manner in which that data is represented, the learning algorithm being used, the space of possible hypotheses for the function, possibly including an a priori probability distribution over those possibilities, and also often an action based on the function values, which may bring the learning algorithm into propinquity to a cyber-physical system or the steam automobile or a nuclear reactor, etc. We've seen recently that deep learning seems to have decisive advantages over more rule-based methods such as regression or support vector machines or Bayesian networks. There have been successes in recognizing objects, faces, spoken words, translating from one language to another, self-driving cars, etc. But I see a number of issues of concern with respect to the use of deep learning. First of all, very large training sets are needed. Secondly, it's not clear that there's a well-defined function being sought, being inferred, because the different experts may differ on the classification of the inputs to the training set. So there's a kind of issue of gathering data from many sources that may, to some extent, conflict. There's the issue already raised that the problem of choosing the most probable function in a deep net is a non-convex optimization problem with all the difficulties associated with that. But another issue is the issue of comprehensibility. If you get a very deep net with a huge number of neurons and 150 layers or more, and it succeeds in the classification process, what have you learned? What are the fundamental features? How can you get your mind around what the deep net is doing? And if you really can't compactly specify the performance of the deep net, you're susceptible to adversarial attacks where an algorithm might be able to construct examples where the net is faulty, gives the wrong result. There are issues of safety. If you don't have a specification of what the net is doing, how can you guarantee that it won't go wild and mess up your nuclear reactor or automobile or the robot that is being controlled by the decisions of the net? So there's the issue of safety, and there's also the issue of rigidity that unlike human learning, where you learn concepts over time in a variety of environments with more and more examples eventually making you more and more expert. Here, the format is sort of frozen. You have a function with a given domain, a given range, a given set of examples, and so forth. And so it's a rather static model in which there isn't a lot of autonomy or plasticity. So the model certainly doesn't correspond to the way that humans or biological systems learn. And I'll just conclude by mentioning that there's an interesting call for proposals from DARPA in which they ask for the development of next-generation machine learning technologies that can learn from new situations and apply that learning to become better and more reliable while remaining constrained within a predetermined set of limits. So this is learning on the fly rather than learning from a fixed training set. And I think many of the applications in the future will require that flexibility and adaptability.
Bravo. Next we have Marina Meila, who might not have prepared enough for this, but no, I'm just kidding. She has a couple of slides. Statistician and data scientist from University of Washington.
So I made slides in the hope that I will talk less if I have slides. What makes me thinking more than everything is that computational challenges, in machine learning at least, seem to always come with statistical challenges as well. And to give just a few examples, if the data is so big and divided on so many computers, can we really believe that it comes from the same distribution or that it is identically distributed? Or that we have removed from it all the dependencies that may exist because of the way the data was collected or the way the data continues to be collected? Oh, thank you. Shall I start again? Is this on?
Yeah.
Okay. So I will not belabor this point. I want to also stress that this is not always a curse, it's also a blessing, because there is accumulating evidence from various parts of machine learning that sometimes easy data helps with, implies easy computation and the other way around. And when I say easy data, it means that the data somehow fits the task we have in mind for it. So one example is in classification. When the classes are separated, it is known that there exist low noise conditions which allow one to both learn fast and to learn from few examples. And more generally, when the data fits the task, one can prove that the learning rates are faster. And this has been proved also in supervised learning tasks. Now, of course, it doesn't seem to be a time to think of easy data when we can learn on hard data as well. So the second point I want to make is that there are two ways of learning, or two objectives of learning. One is prediction, and in which I include prediction on what's the next action, so learning to act, and explanation. And the difference between prediction and explanation is that in prediction, any model that does well is satisfactory, whereas in explanation, we want somehow that the description of the data be unique, or that we have very few descriptions of the data that are competitive. Otherwise, we can't call it an explanation. What I see today is that prediction is, from certain points of view, solved, but explanation is not. Like, the problem of explanation is much further behind. And I see this as a big challenge, both in terms of statistics as from the point of view of computation. Like, they cannot go separately. A related question that you may ask is, do we need explanation? Why? If you can just predict, why do we actually need to do any efforts to explain what we are seeing? And I argue that there are some reasons to do that. Ask me later. And finally, I think a big challenge, again, both from the statistics and the computation point of view, is validation, validating the models that we have learned. And thank you. So I made this slide, and this is the purpose of the talk, to see how, and this is very approximate, please correct or add to it if you would like, where is machine learning most successful, most pervasive, and where it's not. And it looks like on the left, at least in my opinion, machine learning is actually in the driver's seat, whereas on this side, it's not so much so. So what's the difference between these two? On the left, I don't know if you see the right. It's easy to validate the results. We can tell when a speech recognizes words well fairly easily. Of course, we have test sets, but in the ultimate reality test, it's easy to tell whether we are doing a good job on the left-hand side, but not so much on the right-hand side. In physics, it can take decades to validate a hypothesis. And from the point of view of what's happening on the right-hand side, machine learning is really not so useful. Machine learning can generate hypotheses very fast. But when it's expensive to get labeled data because you need to have a trained expert to give you just one labeled data point, then machine learning is not doing such a good job. And we need to think of how to actually both generate hypotheses and validate hypotheses. So do the human job of testing scientific hypotheses and testing explanations. And I think of this as a computational challenge because of this, in the large size of the data, it is hard to apply the statistical methods that we have for smaller models. In a second aspect of the validation is that when we have a large trained model, and this has been brought up most recently by Dick just before me, it is important to also validate the results, and we have to be more creative. Again, we can't expect classical model selection or model validation to work, but we have to be able to actually computationally find methods that at least locally can tell us whether a data point or the next prediction is trustworthy or not. And this is all. This is the end of this.
Finally, we have Mike Jordan from Berkeley, which has led a few movements within machine learning. Let's see what he thinks is coming next.
Yeah, so I resonate with a lot of the issues we talked about already. I don't think it's so much a computational issue, though. I guess the framing was, what are the computational issues? And so I would actually disagree with it about the convexity story. I think these deep neural nets are not hard to optimize. You can get them to zero error with no trouble. And I think if you have a wide enough one, there's lots of paths. And I think there's even some kind of folk wisdom that there's a paper, I think, that from every point there's actually a downhill path to the global optimum. So I don't think it's actually that there are a lot of problems there, but I don't think that's necessarily it. I still think it's all statistical. And I think I resonate to what a lot of Marina said. We've borrowed the mathematics of statistics a lot. And we learned about covering numbers and so on and so forth and risks and so on. But we still don't think like statisticians. So we don't think about the data you gather today is probably not likely to be much like the data you get tomorrow. There's lots of changes, lots of biases. How was it sampled? Probably it was not sampled IID. Probably it's not a random sample. If you don't take that into account, you're going to make the wrong decisions and wrong inferences. And you'll, of course, if you validate, you'll find that out, but maybe it's too late. And so, we've been developing machine learning in systems like search and vision and speech, where if you make an error, it's just a little bit of a pain. Someone gets a little annoyed. But if we're deploying them in finance, in medicine, in transportation, and so on and so forth, errors are going to be deaths, and errors are going to be chaos. And so we're not ready for that world where we really have real confidence intervals on our outputs. We have these black boxes that give out an answer, right? And hardly anyone is talking enough about, well, are you sure about that? How sure are you? So if you're going to go into the doctor's office in the future, the doctor will take your genome in addition to all your vital signs and all that, and they'll put it into a big system, that used machine learning. That'll have done all the data from all the other people, and maybe people like you, hopefully, not just random people, and all the results of and it'll come out and say, the doctor will look at it and say, the neural net output a number which was 0.62, and any number of 0.6, you have to have a liver operation. All right, what are you going to say? Well, you're just like a current CEO says. I'm not going to try, tell me there's, how that number rise and what are the confidence intervals? And if you say, well, the confidence interval is huge, I'm going to say, well, can I get more data? Oh, yeah, you better get some more data, and so on. So this is, to me, the issue. It's building systems that are able to respect those kind of uncertainties, making decisions. So, you make a decision that in this image there's a cat, and you make a decision in the next image there's a cat, and so on. And you do that for days on end. Well, your error rate is now uncontrolled. For each decision, maybe you have a calibration, that your error rate is something. But what about an ensemble of decisions? And what about when the decisions are all related? which is the real life. Most decisions are related in various ways. Well, we're not talking about that. So anyway, statistical people talk about this a lot, and I keep my role in machine learning is keep people away from the idea this is just computation. This is inference, folks, in decision making. And so you got to think like that. You got to think about my data set actually came from something out there. How did it arise? What am I trying to say about things out there in the world? And let's not just borrow the techniques and the math and the theorems and all. Let's think about the whole style of inference. Also, we talk about control. We're all kind of starting to get more now towards active things and control and all that. Well, control assumes you know causes, right? Because if I just have a bunch of variables to wiggle and I have some desired outcome and I wiggle that and it doesn't cause that in any way, they're just correlated, well, I can wiggle it all day long and nothing's going to happen. And people assume you already know the vector of control signals. And you wiggle it and you see what reinforcements you get at the end. Well, in real life, you don't know. You're a public policy planner or city planner. You don't know what variables to change. Should I put a stop sign there or whatever? And so you've got a reason from your data to do causal inference. And again, there's a whole field of that. In machine learning, we pay far too little attention to that. Because if you're going to do control, you've got to know the causes. Right? And then if you do control, you better worry about all the stability issues, all the unmodeled dynamics that you're possibly exciting by putting your control in there. Because stability in systems that are time critical and are death critical is going to cause chaos. Right? So I just think we're way unprepared for this. And I also think maybe my last point is a critical issue we have to face in this community is how to talk about our work without all the hype. And how to take on projects that aren't like AlphaGo that's sure to create a storm of publicity and then a storm of discussion about future robots taking over and a storm of talk about how intelligent everything is when we know it's not, which is nonsense. And just a storm of things that have nothing to do with the real problems is that we're about ready to build big systems that go out and get deployed and are going to cause lots and lots of problems. So let's take on problems that aren't AlphaGo. Let's take on real problems that have to do with water and health and climate and stuff like that aren't going to go into the New York Times, but are rather going to make a real impact on real lives and make our world a better place. And not go for this, we're the glorious new wave of exciting computer scientists who are going to create superhumans. So I think we've gotten taken over by that spirit of it's got to be this super grandiose thing, and I don't recognize it. This is not the field I want to be in.
Let's thank the panelists for these. Now we'll just go one by one and ask questions, starting now. It's open for it.
So I have a question that. So I was the moderator for the last panel, and I got criticized afterwards for not asking the following question, and it's been come up a lot. So I think it's good to ask. The question is, what role, maybe even especially in the short term, should theory have in this kind of current empirical wave of machine learning?
My talk yesterday was that's how I started the talk. And I'm trying to reassure all the young people in the room that actually most of the cool problems now are theory ones. So the ones that he was alluding to with communication, for example, those are theory problems. When you start to have asynchrony and distributed and communication issues, all the classical guarantees for matrix completion or regression are out the window. So those are all wonderful, important theory questions. And then all the things about how do you get confidence intervals at scale and how do you do things in a temporal way, how do you get causes, those are theory issues. If you just do it and write something down and try it on a test set, that's not what the next generation of people want to see. They're going to see that you thought out the formal structure of the problem and you pieced it apart and you can now build systems based on it. So you really think that all this empirical wave, that the next generation of young scientists or young people like ourselves are going to come along and say, oh great, they succeeded, that previous generation, at making a robot work. It's all done. Machine learning was solved. Let's go on to other things.
No, but the reason I don't find your answer completely satisfying is because it feels like there is just, it feels like there is kind of the empirical wave seems to not really be paying attention to theory and really considering, and they are just content running SGD for everything, and they are content just increasing the size of the net, and they are content just kind of adding band-aids. And
when there's huge numbers of training labels, right? They're not content if they don't have lots of labels, right? They don't know what to do in that same case.
Fair enough.
Matusai,
I would say that a lot of the hype that is currently generated is because a lot of it is driven by companies like Google, and these companies are basically treating it as a playground. It is not what they sell, you know, like what they really depend on. They're not using neural networks, but okay, so they will vary something here and vary something there. I think that a lot of it has to do just with the expectations. So one of the acronyms that I really like the least is AI, artificial intelligence, because we have no idea what is intelligence, and therefore artificial intelligence, you know, it's not. I like a slightly different term, but that is much less exciting, IA, which is intelligence amplification, which is a real term. I haven't invented it. And it's basically the idea that we use computers to enhance our ability to do a lot of the drudge work for us, but at the end it's our decision, right? So the problem with that term is that it's hard to excite young people about it. That's really the problem with it. But I think that it's still a very valid term. And then when you look at it from that angle, you know, work like how do you estimate the mean and variance when you have a large fraction of outliers, that's important. So I think a lot of the kind of overhyped excitement is because now everything is AI. Now everybody is using AI. Maybe even people are not really changing what they did, but now they call it AI. So.
Go ahead, Mark.
Just a small thing to add, at least from an optimization point of view, what theory can do is to, for example, help us understand and justify some heuristics that are used in practice and seem to work very well. And then when we understand them, for example, why is it that they work? What is it about this class of problems that seems to make them much better than what worst case theory says? Then we can improve these heuristics and we can apply them more robustly. So there is a lot of room for theory.
I want to add just one short thing, that before we wanted to understand various other data sources, and that was the job of machine learning. Now we have also neural networks as additional data sources, and the job of theory is to understand this new process that we have created, just as we used to understand the others.
I agree all that's been said with all that's been said, and I would just add that when you start dealing with safety critical applications, controlling robots, health systems, driving a car, and so forth, you better have firm theoretical guarantees of the performance to understand that your system is not going to go wild.
Questions. Wanted to ask if you feel that there is also a need from theory to come up with new definitions. That somehow, before we try to prove theorems about all the issues that you mentioned, whether maybe we don't have the right models or like, you know, what kind of questions we should ask that are suitable for a rigorous answer.
Yeah, briefly. Yeah, I think that actually, at least again in optimization, that's definitely the case, that we need to formulate the questions better. So what property of an optimization problem that is not convex seems to be making it easy? And also when we say we want to find a solution, what are we talking about? What kind of solution is of interest? A global minimum, a local minimum, a kind of local minimum? Do you want to differentiate between different kinds of local minima? It really depends on what you expect this solution to then do. For example, you're training a model, and then you want to use this model, and maybe you want to judge it by its generalization. So, so all that we should work it back and see what do we expect from the optimization algorithm based on that. So I think clarifying the questions itself is very important.
I have one advice about coming with new models is to actually work on applications. So that was my direction in the last few years. I've been actually going and working with people from the sciences on problems that they have. And you know, the downside of it is that some of these problems are kind of easy, and if you just understand regression, you can do them. But quickly, you get into these problems that how do I analyze data that is so huge? How do I even pick the examples that I should train on? And how should I think one of the things that I found the most revealing is, in many cases, you cannot think about machine learning as an independent entity. You have some process in the lab, and that process involves decision making. Let's say finding microcrystals in droplets, okay? And you want to make that decision process more efficient, and you want people to trust the updated decision process. And so we fit in something like boosting, but really the most important thing was to decide how do we change the process going on in the lab in terms of many small decisions that have to be made, so that we really give them a benefit. And from that, I think you can go back and come to active learning and interactive learning and kind of thing that Shanjo is interested in.
There's a concept in complexity theory called smoothed analysis, as you know very well, which might possibly be applied to validating some of these supervised learning schemes. The idea is to show that even though your net or your solution method may have errors, it's correct almost everywhere. That is to say that if you take any data point and perturb it randomly slightly, then with high probability, you'll get a modified data point where the solution will be correct.
So it sounds like we mostly agree that there's great danger if we are using these models in ways that we don't fully understand, especially in like the realm of healthcare. And also, I think of the recent example where there's some sort of machine learning algorithm that's being used in sentencing, judges sentencing, and that's like extremely racially biased. I got a copy of this article about. So like, as our community is like putting out these models that we don't fully understand, and people are applying them in ways that they don't fully understand, like obviously problems can occur. So what do you think are some like best practices to make sure that we're using these models in, I guess, the best way possible, and like what's our obligation as like the community of academics, like creating these models to make sure that they're being used in ways that provide the most insight and don't have these other consequences?
I think that one of the most important things is to be very careful about the data selection process and the data labeling process and the evaluation. So those are kind of things that you and the potential user should agree on. These are the ways to do it. And then when you go forward, you actually are going to use those processes to make so that your statement that at the end of the day that this works is justified statistically.
So I think right now, hearing your question, that this is a great research question, and perhaps online learning would have something to say about it. How to validate a model like after it is deployed? How to actually continue exploring to estimate the model's error while the model is actually in current use?
Can I frame this as a societal question for a community of scholars? And this has kind of come up, a number of you have talked about safety, but I want to ask it just in terms of the progress being made in the field. And historically, other communities of scientists, for example, physicists at Alamogordo with the bomb in 1945 had to grapple with the impact of the bomb. Genetic engineers in 1975 with the impact of gene editing literally stopped doing research. And I have this sense that this community, despite what I think Mike said about the lack of quick progress, might be on the verge of its star turn in terms of having a big impact on the world. And so, do you think that the responsibility lies with the society around you, or do the individual researchers of the community itself have a responsibility for the consequences of your technology?
Well, I think we're far from the level of understanding those other communities had, so that they could actually track forward consequences. We're really far from that. I think though taking responsibility for some of these things and admitting that it's a research problem and so on. So just the fake news epidemic was to me shocking and real and still ongoing. And I was pretty disappointed in Mark Zuckerberg standing up and right after the election and sort of saying, well, it's not our problem. We're just trying to put the stuff out there. Well, no, we should take responsibility. Our algorithms are changing the world at some level, and I don't think it's leading to chaos necessarily immediately, but we have to think it through a little bit. We have to say, well, that's a research problem. And yes, we have to partner with lawyers and with sociologists and all kinds of people. We're not just a little microcosm. So we have to take responsibility for being in a whole technological infrastructure with other people and not just be our little computer scientists writing our algorithms and putting out our code and thinking that we're going to make the world better, period. So there's a whole Silicon Valley ethos that a lot of us have sort of absorbed that, we're shaking the world, we're doing all this novel stuff, and then the consequences be damned. So I don't think we're at the point where the historical examples you gave were much more there was an imminent danger. But just this honesty and, like I was talking about, let's be clear on the dangers, let's be clear on the uncertainties, let's be clear on all that. You don't get that when you hear a lot of the stuff people talk about machine learning as soon as we start to transition out there to the outside world. And yes, it's partly, Yoav, a good point. How do you excite the younger generation? Well, we've overexcited. We've got them overheated. I go to China now, and they just think that we're, that artificial intelligence is now everywhere, and it's just we've solved it, and they just want to get in and cash in on the thing. Just to pick on that point too, which I totally resonate with. Take machine translation, which has definitely gotten way better, and Google is now apparently doing with neural nets, and it's gotten even a jump in performance. And so you have a lot of people sort of saying, well, that problem's nearly solved, kind of like speech, it's commoditized and everything. Well, yes and no. If just from a pure copying what humans can do, taking a sentence in and copying it over, it's not solved even there, but it's kind of becoming useful. So you can build companies around it, right? Well, I speak several languages, and I just know that I did not take in trillions of sentences in French and trillions of sequences in English, and then I learned a neural net to map between them, right? No, I have a semantic representation of the world, and I listened to the sentence, and I understood it, and then I kind of take it out in the other language. And so, just building maps that mimic what the data is out there is not understanding. It's not intelligence at all. And so as we get into these things like dialogue and real natural language understanding and question answering, we are not doing intelligent things. And yes, part of it will show up with the lack of robustness of these things. Translation is not particularly robust. Dialogue will be horribly non-robust. And we just got to be honest about that we don't have intelligence yet. And so I kind of actually resent that it should have been called statistics. Then it got called machine learning, fine. But then it got called AI. And I agree. It was all about IA. And now suddenly everyone's calling it AI as if we've solved the intelligence problem. Well, we haven't. We're using stochastic gradient descent with huge amounts of data. We didn't understand anything.
I want to echo everything what Mike said. I just want to add that it is an interesting paradox that in, let's say, machine translation, large neural networks are being trained on Wikipedia and TripAdvisor and other things. So it seems that there is a model now of large companies using what well-trained humans do in their free time. So basically using the small number of humans who are well-trained and their free work to actually make profits in some sense. And this is a very interesting model. I haven't seen it anywhere else. And it would be an interesting look at where this is going after all.
We should have paid for it, right?
In the early days of genomics, people in the community formed a committee to set up guidelines for certain kinds for deciding which genetic manipulations were too dangerous to perform. And it would be more difficult to establish guidelines in this field because of the extreme diversity of applications. But certainly when machine learning, the outputs of machine learning programs are being used to control cars or cyber-physical systems or medical procedures, it might be necessary to get the field to agree on some standards of safety before proceeding freely.
This is actually similar to the question that was just asked. And I think, I mean, in some sense, you're right that the whole artificial intelligence thing, there's no intelligence going on, but I think that's really not the point. The point is that the technologies that are being developed could really affect society in a way very similar to how manufacturing technology affected the textile industry 200 years ago, where there were textile workers in England who, because of technology, started rioting and causing great societal unrest because they were out of work. I mean, in some sense, Uber is right now exploiting the drivers so that they can become profitable, so that they can then develop technology for self-driving cars that will then make all of these people who are right now the bedrock of their profits redundant and out of work. And at the same time, they're not developing their own skills so that they'll be useful in the future. They'll be basically out of work cab drivers with no skills because they've spent their several decades or however long working on something that is now redundant. And so I guess the question from a theoretical computer science perspective is, I mean, so we talk about like confidence intervals in statistics, right? So let's say, for example, you are able to understand confidence intervals based on real data sets. That has nothing to do with the fact that there might be a lack of social acceptance of a decision that's made by an algorithm that's not a human. And so humans will want to hold responsible an entity that makes mistakes somehow. Right now we have humans who are making these decisions, and you can actually go and you can blame your doctor for diagnosing you incorrectly for cancer. But when you have algorithms that are doing that, despite how small your confidence intervals are, that could create, those are new challenges. And so the question again is there any way of formulating this from a mathematical perspective? It seems like these are challenges that may be beyond the ability to discuss mathematically at all.
So I would like to just give an example to just show that yes, you can actually do that, and that there will be acceptance eventually, and that it will be a good thing. So I worked with pathologists, and they do analysis of prostate biopsy. And prostate biopsies, and in case you don't know, they're huge images. So they're basically 20,000 by 60,000 pixels. A pathologist, a trained pathologist, would look through that slide in about half a minute and decide if there is cancer. There's just no way that they can actually look at all the details, right? So they have some heuristics. Hopefully their heuristic is good. On the other hand, if we train whatever neural network or support vector machine to detect cancer at the very minute case, what we can use that for is basically just to direct them to the places where they should look and make their work more efficient, right? So I think that in a lot of cases, not in the car driving, I don't think that that's really. I'm not a big believer in that endeavor anyway. So, but in many decisions that have to do with analyzing medical records, analyzing medical photography or EKG or EEG, people are doing it now, and they're doing it as best as they can, and computer can do it better, and computer can actually point out the phenomena that the human would agree that's really the right phenomenon. So. It's true that humans want to keep the control, and in my IA approach, that's what I'm saying. You are continuing to analyze this, but now I'm making your work more efficient, or more accurate, or whatever it is. So I think that there's just kind of less alarmist ways to think about these things that actually can produce useful products, and basically be good for the world. I think that when we talk about the kind of really alarming things that technology is doing, like for instance Facebook. Facebook is a great thing, everybody can talk with everybody, but then it also gives bad actors new opportunities to exploit people. So it's a complicated decision, whether should we disallow Facebook or should we regulate Facebook maybe? But all I'm saying is that these are not technical questions.
This requires a big dialogue beyond our room, right, about jobs and job displacement. But so one point I'd like to make is the speed has changed. So the Industrial Revolution was sort of like 30 years for people to adapt. And I'm not sure I agree with the comment that I would be a little alarmist here. There's a lot of jobs that could be lost much more quickly. And so, yes, all the people driving, I actually am glad because there's 40,000 deaths a year, we can turn off those deaths, with self-driving cars. That's great, but there's a lot of jobs lost really quickly. So then what do you tell them to do? Well, you become you go into call centers. There's kind of a typical one. I don't know many truck drivers who'd like to be in a call center, first of all. But in 5 years, the dialogue systems will still be crappy, but they'll be good enough you can get rid of lots and lots of call centers. And then where do you tell them to go 5 years later? So it's not 30 years to adapt. It's really, really quick. So that, to me, is the big critical difference. And so, yeah, we got to be part of the ongoing dialogue about where we really think our technology can go, on what time frame, so that people can start to adjust and have real serious discussions about it more quickly, and you can provision. I'm not as alarmist in the long run, though, because, society has adapted again and again and again to waves of these kind of things. An example someone mentioned was massage therapist. Is a job description. A lot of people like a lot of money be massage therapists. 100 years ago, there was no massage therapists. It did not exist, right? And there will be brand new jobs created, that we just can't envisage at all, that seem kind of stupid now. But the idea of someone sitting behind a wheel right now and sitting in a piece of metal hurtling along a highway, that's kind of a weird job to have. Some level. So I think new ones will be created. They, in some ways, could be more interesting. But we got to think about it really overtly. And so, not to return to this thing, but, talking about the killer robots and, super intelligence taking over, there's just so much discussion of that's fine. That's science fiction. Yes, in 400 years, that will be an issue. We should talk about it a little bit now. But you're absolutely right, much more pertinent problems.
The science fiction part is a separate issue than the social unrest issue.
I know, but
you can sort of rest on the necessity being the mother invention and wait for the mother invention to occur because of the necessity.
Yeah.
Or you can sort of actively try to avoid the underlying, the inevitable social unrest that could occur.
Yeah, so we got to be careful, slower, less greedy, more social. It's kind of, I don't know how we're going to get all this because our society seems to be going the other way, but maybe emerging countries. The U.S. has screwed it up. Maybe China will help.
To ask a more optimistic question, this wave of machine learning successes is very exciting, even for somebody who doesn't understand it or practice it. Has it revealed to you anything fundamental about computation itself, about the nature of computation, a surprising new algorithm or definition? Or here's an insight that I didn't know.
I just think we don't have computational lower bounds. Complexity theory delivered something very useful for certain other fields. For this field, it didn't really yet. And I think that our notion of what the model is for both getting upper and lower bounds needs to be average case. It needs to be specialized for certain situations. Why has optimization theory played such an important role? Well, because there's lower bound oracles that are much simpler computational models that actually match the upper bound rates, and that's been a very, very important thing to do. So I think computation as a field emerged in an era that it came from logic, and you wanted to solve the computability problem of what things can possibly be done, and what is the polynomial exponential barrier and all that. And we're just not in that world. We're in a different world. So you need other kinds of models that are, and let's call them average case, but that doesn't even do justice to them, but models that are more specialized to certain situations that give you more interesting, tighter theory that's more relevant.
So computational complexity theory has chosen to focus on worst-case analysis, which makes its findings rather irrelevant for situations where experience shows that the perils of NP hardness really don't occur in practical situations. But there has been no theoretical framework proposed that really successfully replaces the worst-case analysis. There have been attempts at average-case analysis, but the average case models are too simplistic to be really interesting in applications. So I think there's a real challenge to define models that are more optimistic than worst case and yet not overly trivial in their formulation. It's an open question not only for computational learning theory, but for all kinds of combinatorial optimization.
But is that really so? I mean, there is in optimization theory lots of average case analysis that's gone beyond. Originally, there was Nemirovsky and Uden, which was worst case, and that was very useful. It's still good bounds. But now we have a whole bunch of other models which are average case that are, it's not for all of computational complexity and all combinatorial problems, but it's for certain classes of optimization problems. Been very useful.
So kind of to that end, I mean, the taste of the community broadly has been to come up with sort of lots of regularity conditions on the kind of hypotheses we're willing to use for the models and for the optimization procedures that we're willing to use. But part of the sort of like deep learning story has been that people sort of throw stuff against the wall and it sticks. And even though, strictly speaking, these things might be in some very difficult complexity class. And a lot of this feels like it comes from the fact that we are willing to make or can make many fewer assumptions about the data, like the properties of the world, right? And one of the kind of examples of the success of that is like convolutional neural networks, where people are willing to say that, if I translate my image around or something, that doesn't really affect the semantic meaning of this image. Is there any hope for us developing theory about sort of the properties of the data itself across many different actual domains? It's kind of like the average case situation, but I don't know, are we completely, is there kind of any hope of this?
A theory of data?
A theory of data, yeah.
Well, I mean, there's a long tradition, and Eric Lehman here worked on this sort of thing at Berkeley, where you suppose you have group actions on the data, right? And so the data forms a set of points which can go under group actions. And the estimator should go under the same group action. These are called equivariant. There is a whole, and people are starting to return to that with some more interesting groups that are being studied, not just translation and permutation groups. That is exactly a theory about data that turns in then to constraints on your estimator. You're sort of limited in the old days, but especially if you go to Fourier analysis on groups kind of things, you can get a much richer class of operators.
That's okay when the data is in d-dimensional Euclidean space, but what if the data consists of utterances in a language? How do you get a reasonable model of that class of objects?
I just want to add that there are various modeling assumptions like that. For instance, good old Bayesian networks are a way of describing the data that is very flexible in some sense, and everything is on top of it. And somehow, interestingly, related to the previous question, a problem that is hard and it actually is hard theoretically and is hard to approximate is inference in Bayesian networks. When we talk about models of computation, so we can think it is good to look at what other progresses have been made in other fields. And machine learning has been very good at doing that, like looking at optimization, looking at GPUs and so on. And we should probably look at the recent success with set solvers, which is essentially a way to solve many NP-hard problems easily and build our new computation models based on progress in other fields of computation.
I guess along those lines, I would ask to what extent do you see deep neural networks as being excessive in that they're representing distributions that are much more complex than data distributions empirically should be, right? And I guess this sort of speaks to the idea that optimization tends to work well, and some of the other heuristics involving regularization.
Are deep nets too complex representation?
Yeah. I mean, the computational challenge is really just conceptual challenges that we don't understand the data distributions well enough to come up with more reasonable models.
That's probably true. It's certainly true that the deep nets that are being used successfully in these applications don't have very much explanatory power for us humans. We look at them and we have no notion what they're doing, what features they're representing, whether they can be simplified without losing their effectiveness. It seems, they do seem excessive somehow.
I want to say that I see it as a problem for the future to be able to measure how much overparameterization a neural network has after it has been trained. But interestingly, in statistics, it has been known for a long time that to predict well is not the same as to find the model of understand the distribution of the data well. In fact, if you want to predict well, you have to in some sense, you have to over-parameterize for any finite sample, or unless you are in sufficiently large sample, and sufficiently large is not known. And so this is what I see as an interesting paradox, that one cannot explain and predict with the same model in many, by theoretical reasons in some sense.
Final question after you.
So I think one way to think about it is in terms of scaling. So there's a trivial way to learn, which is nearest neighbors. And basically, you just store all of the data, and it tends to work pretty well. Now, the problem there is that the amount the size of the representation is the size of the data. If you're talking about neural network, I would say that I would really be convinced that it learns if the number of parameters that you need stops to increase as the amount of data increases. Right? Basically, hopefully if it becomes smaller, but definitely that it should not need to increase. And it's a hard question to kind of do practically, because we're just doing some local search and finding some solution. But in principle, what I would say about such a model is the question is, can you find a low-dimensional representation? So can you find something that does not increase, so you have basically the size of your model does not increase linearly with the size of the data?
They can be sparsified, right? Dramatically.
What?
A learned neural net can be sparsified dramatically. I mean,
right, but the question is still, how many non-zero parameters would it have as you increase the amount of data?
They're non-zero and binary at this point, so yeah,
whatever.
It's a huge compression.
No, I'm not saying that it's not a compression. I'm I'm just asking about the scaling. You can compress also nearest neighbor.
Question from Sanjay?
Okay. So many of us here are in academia, and I think we have this common experience that now there are these hordes of students who really just want to learn about deep learning. Okay, and I think as responsible scholars, most of us what we've been doing is making sure they get all the fundamentals and they learn about all the various aspects of machine learning before we finally arrive at that one lecture about back propagation that they've been breathlessly waiting for.
Last lecture.
Yeah, the last lecture of the club. But so I think that's well and good, but I can't help feeling that in the current context there is some other stuff that we also need to be teaching them. Something about the I don't know, like societal impacts or or these sort of things, which are really not part of the standard machine learning community, the standard machine learning class that that the community as a whole has developed. And so I was wondering whether any thoughts on what those things should be and what form it should take.
I mean, the causal inference is just take an example. We don't teach that. I bet do you teach it in your class? Yeah. I mean, I don't see any machine learning class out there to teach it. And for like medical domain or anything, it's all about, I measure various things about your body. I give you a drug, and did the drug have a causal effect on your getting better or not? Right. So that's critical. So how can you do causal inference? Well, here's one way. You do nearest neighbor. So the core problem of causal inference is not just a gradient descent on a loss function problem. It is you can only give me the treatment or the control. You can't give me both. If you give me both, you can just subtract and you get the causal effect. You can't, right? So you only give it to one or the other. But if you happen to have a twin Mike Jordan there who has all my same properties, right, you can give one to him and not to me, and you get subtract. Right? So if you do nearest neighbor, you can find a doppelganger for anybody, hopefully nearby in space or someone just like them, and they happen to have gotten the treatment and you got the control. And if you pull all of those, you're not going to do regression, and you can analyze it, and you can do all kinds of stuff, right? So I just taught it to you. You could teach it. We could teach that to freshmen. But somehow we're not being motivated to teach that, and they get excited about that because they can do actual causal inference in the world. That's actually somehow as exciting as taking an image and saying there's a cat in it. You know, so I just think we're we don't have the imagination to actually think of the other classes of problems. But I think that's damn word AI is hurting us because the students come to class want to learn about robots and vision and speech and language, right? They don't want to learn about the bigger, broader kinds of causal inferences that we want to make in the real world setting, not just our infrastructure, but our sciences, as Marina was alluding to. And we just got to get people oriented. Those are super exciting unsolved problems, and they are scientifically deep and so on. So, also just teaching an A/B test. So if you look at Berkeley, we designed a freshman level class, and we call it data science because that was the term of the day, but it was avowedly not a machine learning class. So one of the things you do if you go into industry on day one is you have to do an A/B test. You know, very common. We had our current website. We get 10,000 hits a day. We changed the website to have red pixels over here, and we got, you know, not some other number of hits, right? And you get 2 columns of numbers, old website, new website. Is it worth investing $5 million to change the website? Well, it's a question of whether those 2 columns of number are different or not. How would you solve that, right? I bet you don't teach that in your machine learning class either. And I bet, you know, most of my machine learning classes wouldn't even know really how to do it. They might say, well, you do a t-test. Isn't that the right thing to do for things like that? Well, no, there's the permutation test, which is that if they really were coming from the same distribution, these 2 columns, you could stack them together in one super column. You could permute it randomly, and under exchangeability, you break them into 2 new columns. You're in the same distribution. You can do that over and over again. You're getting the actual sampling distribution of some measure of difference between the columns, say variation distance. Now you can ask whether your original difference was in the tail or in the middle. So I just taught you A/B testing on the permutation, and freshmen can understand that. And they can program it in Python, and they can try it on real data and make inferences about, is the population in this county the same as the population of the juries in this county? That's a cool social science problem. You know, so I just think we should be getting out of the AI. I mean, I hate to say this, my AI colleagues are all excited about everything they're doing, but we should not just be in the AI subworld. We should say that we're broader than that. We're in the social science world. We're in the rest of computing world. We're in the communication bandwidth limitation world. We're in the physics and biology world. And, you know, so I wish somehow the journalists would go back to using ML instead of AI, because it really is a way broader enterprise and more exciting to lots more people.
Any more final thoughts from the panel before we close? We might have to keep it short, since it's our time now.
Well, just 2 points actually. So 1, not 3, but
let's stick to 1.
You know, just to comment on your point. So I mean, Thomas Richardson has a class on causal inference. He's been teaching for over a decade.
He's a statistician.
Yeah, but it's a class on causal inference.
I know, but the statisticians are all over that, and the machine learning we're not.
It's a cultural
divide.
science. It's about computer science versus statistics.
Yeah. It's a stupid cold cultural divide, but it's still there.
To gather students, he
How many students do you have in his class?
Well, he says it's a deep model class, and he brings them in.
Yeah, exactly.
The second thing, actually made was, I mean, you had this paper on algorithmic weakening, which I thought was a really amazing paper, and just conceptually as well as the actual content. And that seems to be potentially a promising way of looking at large data sets and the way in which algorithms behave, possibly, you know, theoretically, as data sets get larger and algorithms or something get easier. And
I think it's all one field. Computer science and statistics are really one field to me. It's the inference problem with data, moving it around, being intelligent about it, and they just happen to get broken apart at some point. But it's crazy that they're 2 fields. So yes, I'll
but would you see that as a paradigm?
Well, you should take the pessimism of the statisticians together with the optimism of the computer scientists, blend them, and work on all these problems together.
Any other remarks? Anybody has any final words? Or otherwise, let's thank the panel.